All right, this is an example of how to calculate a rate law for a one, notice we only have one reactant rate law, and I'm going to show you how to calculate both the order and the specific rate constant, and then in the end additionally write the rate law for the reaction. So this is an example of a decomposition reaction of hydrogen iodide. Will break up into hydrogen and iodine. And you are given experimental data. Notice we've run 3 experiments of which the scientist will get to choose basic concentrations and measure your rates of change in concentration per second. That's typically done by some way determining that a chemical reaction is happening, like a color change, a change in temperature, the evolution of a gas, or something like that. In this example, I'm asking you to write the rate law for the reaction and then find the value in units of the specific rate constant, which also means you have to also calculate the order. So, for example, the rate law expression for that equation is equal to, rate is equal to the specific rate constant, which is little k, times the concentration of HI to the nth power. In this example, I'm comparing two experiments. I'm going to pick and compare experiments 1 and 2. I set up a ratio of the rate laws, and this is my example, so I'm going to compare the rate law for experiment 2. Rate is equal to K times the concentration of Ni to the second power, and I'm going to compare that to the rate of experiment 1 times the K times the constant of HI to the nth power for experiment 1. Where am I going to get this data? From the problem right here, okay? I am going to look at experiment number 2, and it has a rate of 4.4 times 10 to the negative 3. So I'm putting that in right here. That is the rate for experiment 2 is equal to K times the concentration for experiment 2, which is 0.030 molar to the nth power. I'm then going to compare that to the information for experiment 1, which is right here. It has a rate of 1.1 times 10 to the negative third. I'm putting that right here. 1.1 times 10 to the negative third, and this is equal to K times the concentration, which is 0.0150 molar to the nth power. Now when I do this, you will notice that K over K would be, which is a constant, that means it's the same number, they're going to cancel each other out. And I am then able to simplify this into 4 is equal to 2 to the nth power, or n is equal to 2. Therefore, we say that the reaction is second order overall with respect to HI. We just figured out the order. Now I'm going to ask you to calculate K, both its value and its units. Okay, so on the next page, you'll notice to calculate K, plug in the data from one experiment, and I chose to run experiment number 1. Rate is equal to K times the concentration of HI. Notice now it's to the second power because we figured out that order. I plug in the data from experiment 1. Rate is equal to K times the concentration, this is the concentration of experiment 1 to the second power. And then I'm simplifying this, which 0.015 squared becomes 0.000225. Molarity becomes squared. I'm doing this to solve for K. And I'm going to cancel like units. The molarity is going to cancel. And I end up with 4.9, which will end up with a unit of m to the negative 1, s to the negative 1. And if you'll notice here, if you simplify this, this becomes 1 over s, and since molarity is in the denominator here, this becomes 1 over m. I want to remind you that another way to represent 1 over s is s to the negative 1, and another way to represent molarity is m to the negative 1. So there you have it. You've calculated the specific rate constant K, and you've also calculated the order. All right,